Let's jump right into this explainer and talk about something really fascinating. How exactly we price the truly unpredictable in financial markets. We spend so much time in finance hunting for that perfect equation, that flawless analytical formula that's going to tell us exactly what an asset is worth. But what happens when the asset is just incredibly complex, or the market environment is way too chaotic for a standard equation? Well, today, we are cracking open the quantitative analyst toolbox to look at some seriously powerful simulation methods used to model reality.
It all starts with a pretty fundamental problem in finance. Markets are just messy. Standard equations often fall completely short when we try to predict the future, especially when we're dealing with complex securities or those really extreme risk scenarios. Think about it. If you're trying to price an option whose value actually depends on the average price of a stock over a specific period, a simple formula just isn't going to cut it. You need a way to literally map out all the possible futures.
So, to map out those futures, we're going to cover 4 things today: modeling financial uncertainty, normal versus log-normal distributions, the Monte Carlo simulation, and lastly, bootstrapping or resampling observed data. Let's get into it. Okay, Section 1, modeling financial uncertainty. Before we can even think about simulating the future, we have to establish the basic mathematical rules that govern how an asset behaves.
And we've really got to draw a hard line here between 2 incredibly important probability distributions. The normal distribution, which is totally symmetrical, actually allows for negative values. But the log-normal distribution, it's bounded at 0 from below and skewed to the right. And that is an absolutely vital distinction for asset valuation.
Just take a look at the difference here. Notice how the normal distribution for returns, that top curve, stretches way down into negative territory. But the log-normal probability density function stops cold right at 0. This perfectly represents prices because, well, unless things have gone unimaginably wrong, a bankrupt company's stock falls to 0. It doesn't drop to negative $50, right?
So, the crucial point you need to take away is understanding how these 2 concepts are mathematically linked. Basically, if a stock's continuously compounded returns behave normally, the future price of that stock will naturally follow this log-normal curve. That cause and effect relationship right there is the very foundation for using the log-normal distribution to model asset prices in advanced financial mathematics, like the Black-Scholes-Merton option pricing model.
Moving right along to Section 2, the Monte Carlo simulation. Now it's time to deploy the financial multiverse generator.
Once we have our probabilities locked in, computers can generate thousands and thousands of realities. Take an Asian option, for example, where the payout actually depends on the entire path a stock takes over time. Standard formulas are completely useless for that. But Monte Carlo randomly samples our specified distributions to map out thousands of those potential paths that the stock could take. It's like seeing every possible future play out at once. In practice, it's a very rigorous loop. We specify the model and the risk factors, set their probability distributions, and then let the computer draw random numbers. We translate those random numbers into simulated price paths, calculate the payoff for each specific scenario, and then, here's the kicker, we repeat that entire process thousands of times just to find our expected present value.
Now, what you really should take away from this is that Monte Carlo is an incredibly powerful tool, for sure, but it is not magic. While it's absolutely fantastic for pricing complex European-style options or testing how sensitive a whole portfolio is to changing market assumptions, it definitely has limitations. It only provides a statistical estimate. It doesn't give you an exact, flawless result, nor does it hand you some elegant insight into cause and effect relationships. Ultimately, the output is only ever as good as the probability distributions you assume going in. Garbage in, garbage out, as they say.
Which brings us to Section 3, bootstrapping, or resampling observed data. What if we just don't want to invent a theoretical distribution from scratch and risk missing out on real-world market quirks? Enter bootstrapping. I like to call this the great data recycler. Instead of drawing random numbers from some assumed mathematical curve, bootstrapping uses computer simulation to infer statistical parameters straight from historical samples. It brilliantly bypasses the need for complex analytical formulas. We literally just let the actual historical data speak entirely for itself.
Notice how the bootstrap process visually mirrors a true population sample. In a perfect world, we'd obviously love to sample from all possible market realities. But since we can't do that, we rely entirely on the estimated population built from the limited historical data we actually possess. We are generating simulated futures directly out of the past.
The real mechanical secret here is the phrase with replacement.
Because we replace each item right after we randomly draw it from our historical data pool, a single real-world data point, say a really, really bad Tuesday in the market last October, might actually appear several times in a newly simulated sample path. Meanwhile, a super calm Wednesday might not show up at all. And this allows us to build thousands of new, completely plausible market scenarios using only the raw ingredients of what has actually happened in the past.
To wrap up our tour of the toolbox, let's contrast these two heavy-hitting simulators. Monte Carlo is parametric. It builds simulated futures from assumed theoretical probability distributions. Bootstrapping, on the other hand, is empirical. It really doesn't care if the data is normal, skewed, or just plain weird. It strictly reshuffles the reality we've already measured. And both of these approaches are absolutely indispensable for modern risk management and asset valuation.
So I want to leave you with this final, somewhat provocative thought to ponder. We've seen just how powerful both Monte Carlo and bootstrapping can be when analytical models fail us. As computing power continues to absolutely explode and gets cheaper by the second, will simulation methods eventually replace traditional analytical formulas in finance entirely? I mean, why rely on a simplified equation when you can simulate a million possible futures in the literal blink of an eye? It's a truly fascinating shift in how we understand financial risk and asset valuation. Thanks so much for joining me on this explainer, and remember to always keep questioning the formulas.